right, chapter 6 is all about analytic trigonometry. The first section is about the inverses of sine, cosine, and tangent. So let's think back to earlier in this course when we learned about inverses. What are some of the properties of inverses? I would also recommend keeping your unit circle handy. We love a good unit circle moment. So our objectives, we want to be able by the end of this section to find the exact value of an inverse sine function. We want to be able to find the approximate value of an inverse sine function. By approximate, I mean using a calculator. We want to be able to use properties of inverse functions to find exact values of composite functions. We want to be able to find the inverse function of a trig function, and we want to be able to solve equations involving inverse trigonometric functions. And we're going to do it all, hopefully, in under half an hour. So let's review some of the properties of functions that are inverses. So if I have two functions, right, they're one-to-one, so they pass the vertical test to tell us they're a function, and they pass the horizontal line test to tell us that they are one-to-one. So the next thing we need to know about functions is that if I have f inverse, so my inverse function of a function is going to equal x if I use function composition. So if I compose functions that are inverses both ways, I get x. The domain of my function is the range of its inverse, and the range of my function is the domain of its inverse. If the point AB lies on a function, then the point BA lies on its inverse. The graphs of f and f inverse are reflections of each other across the line y equals x. That's this line right here. And in a function y equals f of x has an inverse function, the explicit equation of our inverse function can be found by changing x and y and then solving for y. That will give you your inverse function. These are all things that we know and should be a little bit of a refresher. So here's our sine function. Does our sine function have an inverse? Well, our gut instinct might be no, right? Because it passes the vertical line test, right? But it doesn't pass the horizontal line test. So what we have to do to give it an inverse is we have to restrict it to one half of its period, right? We're going to restrict it between negative pi over 2 and pi over 2. So the inverse of sine of x will only be between negative pi over 2 and pi over 2. So let's take a look. So here we have our sine inverse function. In pink, we have our sine function. In blue, we have our sine inverse function. So y inverse sine of x means x equals sine of y. So let's do an example. Remember that sine of sine of, I'm trying to come up with an example off the top of my head. Sine of pi over 2 is 1, right? This means that sine inverse of 1 would be pi over 2. So whereas for our sine function, we could restrict it so that its range was from negative 1 to 1, that becomes the domain of our inverse function. And the domain would be from negative pi over 2 to pi over 2. That becomes our range from our inverse function from negative pi over 2 to pi over 2. So we're just using the inverse function. So let's find the example of an exact value of an inverse of a sine function. And remember, we're restricting it so it can only have values between pi over 2 and negative pi over 2. So if I want to find the exact value of sine inverse of negative 1, I'm wondering for what value of sine is my output negative 1? Well, that's going to be negative pi over 2, or 3 pi over 2. So sine inverse of -1 is negative pi over 2. Let's work through another example. What if I have sine inverse of the square root of 3 over 2? I have to think about where our inverse was negative 3 over 2. Remember that sine, typically, sine, not sine inverse, sine of theta is going to be our y output, right? So where's the y output? Pi over 3. Well, that's right here. Uh, that's right here at pi over 3, or 60 degrees. So sine inverse of the square root of 3 over 2 is pi over 3, because sine of pi over 3 is the square root of 3 over 2.